Welcome to Module 3 of Surveying 1. We're covering Chapter 4 in the Galani book, Leveling, Theory, Methods, and Equipment. So, there's some terms. Obviously, we need to start with some terms. And this is really zooming out, looking at the true academic side of leveling, which is determining elevations on points. And so here we have, we start with definitions and this diagram, which yes is exaggerated, but it has to really be able to see, to explain this. So the Earth is large. It is basically round. Technically it is an oblate spheroid, but for discussion purposes, let's say it's perfectly round. And when we're leveling, we have to take into account or understand that the Earth is not flat, it is round. On small to even large survey projects, and when I say large, I mean like the average large survey project in the current day is probably a few hundred acres. You can treat the Earth as a plane, P-L-A-N-E, a geometric plane, as if it was flat at that point. But even within a large survey like that, the curvature of the Earth will become something that we have to contend with. Now, this is something we'll really get into more in Survey 2 with state plane coordinates and projections, grid distances, and things like that. But for the purpose of this lecture, we're going to look at the vertical datum that we're probably dealing with is a geoid, which is not exactly mean sea level. We'll come back to that, but it's what we're going to basically consider mean sea level. And then we've got, say 2 points here, A and B. I'm trying to find the difference between A and B, and it's actually going to be, I said in the bigger picture, along a level surface or a level line. And that's a line that's actually curving with the Earth. Think about it like this: the ocean is part of a sphere, but when you're there it looks flat. But if you've been on a cruise ship, you can see ships disappear off the horizon and realize that it's round. So we will take a site, horizontal line is going to be a level line that's horizontal that really does not bend. And it's perpendicular in theory to the center of the Earth. What it is actually perpendicular to is the Earth's gravitational pull at that point. And that's important in some contexts and larger projects because the gravitational pull actually varies around the Earth. So if you were able to very precisely measure the gravitational field and see where it's pointing, it's not always to the same computed geometric center of the Earth. So we're looking through our levels, through our instruments, or detecting things along a horizontal line. The horizontal line will eventually shoot off into space and be just like this horizontal line here. So to go back through some of the terms from section 4.2 in the textbook, vertical line is perpendicular to the gravitational pull of the Earth, and as it says, basically a plumb line is going to pull straight towards the Earth. Plumb line is our best estimation of a vertical line. Level surface is actually a curved surface that follows the curvature of the Earth. The level line is the line that follows that part of the surface. Horizontal plane and the horizontal line are basically right here, what's perpendicular to us at the survey site, our project. We're going to be above a vertical datum. It may be a geoid. We'll discuss datums in a moment. We consider the elevation to be the difference between A and B, which one's higher than the other along the level surface. Think about it, if you're assume that the ocean surface is flat and without waves, and you've got a point that's above, just right on the surface in San Diego, and the difference in elevation from it and a point that's 4 feet below the surface over in Singapore, 3,500 miles away, is going to be 4 feet of difference in elevation, even though it's miles away. And if you were to set up a level in San Diego, it would take a rod height miles and miles above the earth for you to even see it in Singapore. Yet, there's not miles and miles of vertical difference, there's only 4 feet. So we need to talk about vertical datums. First, we want to talk about the North American vertical datum that we've used for a long time, or that we used for a long time. So even going back into the 19th century and before that, the government needed to survey and keep track of elevations, mostly along the coast, because that's where most of the population was. They were concerned about maybe flooding or being above what they perceived to be storm or tide risks. They're still learning a lot of things back then. And there's even something that's not covered in the book called the Clark spheroid, where Clark back in the 1800s had developed, began to do some astronomical observations and developed some formulas for how to define the curvature of the Earth. And according to the book here, the work by the U.S. government generally started on the eastern seaboard in the 50s. And then in 1887, the USCGS, the United States Coast and Geodetic Survey, leveled from the Atlantic to the Pacific. And they also took in some points down in the Gulf of Mexico. And so they did this huge survey project from coast to coast to try to figure out what mean sea level was, because that's a value that everybody could be on the same page, on the same datum. And a datum is just a vertical reference above or below which elevations are measured. So we're talking about a mean sea level datum, and so we call it the National Geodetic Vertical Datum of 1929 because the USCGS published in 29 elevations for all these thousands of benchmarks that have been set around the country. And they averaged, so what they did was they had 26 gauging stations where the tide came and went, and they averaged tide and sea levels over many years and determined where they felt mean sea level was there. And so this big level network that they ran from coast to coast incorporated those 26 tidal gauging stations, and they basically took the average of those once they had ran it. Or my presumption is, I've never studied it, is that they looked at the East Coast and they looked at the West Coast and they averaged those independently because they were on different oceans, and then they assumed that any difference in that from East Coast to West Coast was survey error. And so they balanced them so that what they determined at a tidal station was 0 elevation in San Diego was the exact same elevation as the 0 elevation in Cape Cod, Massachusetts, when actually, because of the tidal motions and which side of the earth we're on or which side of those oceans we're on, they're actually not the same. But that is what we went by in the United States until all the way through my years of high school, until the next one came out, which was basically later called the North American Vertical Datum of 1988. So the NGVD 29 elevations they figured out had some error in it over time, as you can imagine. Big highway projects, more and more railroad projects, better surveying equipment, more and more observations. They figured out that this NGVD 29 elevation wasn't really a good coastal datum or national datum. Now, in my opinion, they could have left it alone and just used whatever benchmarks were around in your area, and you would have been fine to use that as a datum from now on. But they also found that in places there were errors that they introduced due to really old surveying work, and that there was also some changes in sea level. If you look at climate change, we've had extreme hot spells and we've had ice ages. I'm not going to get into the political debate of climate change. But I just say that yes, we have pretty good evidence that the ocean has risen and fallen many times since it was spoken into existence. So they figured out that the sea level was changing and that there is some shifting. The Earth has tectonic plates. We're on the North American tectonic plate. It's slowly moving and tilting and shifting like an iceberg on a grand scale. And so between that and some survey errors that they did not account for, you could find a few tenths of a foot of error even in one county. I've done that where we did a large scale mapping and floodplain survey in the county where I live, and we found as much as a half a foot of error between the old 29 elevations and what's currently there. But so one thing they figured out was these 26 tidal stations did not actually come out to the same elevation. They were locally correct as far as tidal datums for managing the seashore and construction along the ocean in those areas, but they were not really all at the zero elevation. Some of them were higher and lower. So what they decided to do was they decided to run a lot more new surveys and get a lot tighter work, and instead of trying to conform all of the elevations to where all these 26 stations were zero when they really weren't, which is where they interjected error into the 29 adjustment, they decided, for whatever reason, to just take one. It was probably in the middle, would be my guess, but they took Father Point in Quebec, Canada, and they said, okay, that is the zero elevation. And so now, instead of it being NGVD 29, the North American vertical datum of 88 says that is the zero elevation. So the average mean sea level in New Orleans is probably below zero, and the average sea level elevation up around Oregon is probably higher than zero. But they're all tied to the same datum now, more precisely, with the 88. So as time goes on, now one thing that I think is interesting is they started the whole effort to update the vertical datum in North America in 1978. That work took 13 years and was finished in 91. But when they started in 78, they anticipated being done in 88. So the whole project, all of the national publications, everything, called it the North American Vertical Datum of 1988, but it didn't come out till 1991. So we were using NGVD 29 until at least 1991. And that's kind of important because now, these years later, especially since that time, GPS or GNSS has really evolved to where we can do really precise work with it. And geodesists, which are way above GIS and geospatial science, geodesists are like Earth, scientists of a really precise level in the world of surveying and geospatial science. And they have figured out that there's our position on the Earth changes with time due to the tectonic plates and due to some tilts in the continents. And so they all got together, and the new project is called the International Terrestrial Reference Frame. So this is a super complex set of gazillions of mathematical formulas that probably incorporate 2 or 3 levels of calculus, linear algebra, finite math, and 2 or 3 levels of statistics to compute positions on the Earth relative to space and time. So this supposedly should be the one-all do-all. But keep in mind, they thought that they had the one-all do-all in 1929 and again in 1988. So I guess time will tell. But the new datum is going to be called, at least for us, the North American Pacific Geopotential Datum of 2022, or NAPGAD 22. That's what it will be called. So it's not a true survey vertical datum, but it is a geopotential datum, which contains all the necessary information to provide mutually consistent orthometric heights, geoid undulations, gravity anomalies, surface gravity values, deflections of the vertical, and all the other geodetic coordinates and attributes that are related to the gravity field. So the takeaway there is we're after orthometric heights. Now, we synonymously use the term orthometric heights with elevations. So an NGVD 29 published elevation is an orthometric height. So, but it's based on the 29 adjustment of mean sea level. But an NAVD 88 orthometric height is based on that data. And we'll now be using elevations or orthometric heights that are off of NAPGAD 22. Now, this is important because elevations have so many different contexts in the surveying, engineering, architecture, and construction world. You have elevation views. You have, in some places, elevation is simply the difference in elevation between the slab and the point on the building. So orthometric height, though, is a unique term that is unique to surveying. So we tend to use that term. Now, when we get back to curvature and refraction, this is a better diagram, in my opinion, than the one that the book focuses on. And here we're at point A, and our horizontal line of sight departs from the level line, which is basically the surface of the Earth, and that increases as we get further from A. So we talked about the curvature of the Earth, and even though this slide says curvature and refraction, this is the refraction component. Now, you might study this in like physics too, but light rays bend. We'd like to think that light rays are perfectly straight, that what we're seeing is exactly what we're seeing. In reality, that's only true in perfect, moderate ambient light conditions, like in a warehouse or in the floor of a shaded forest. What actually happens is, as your line of sight nears something, the light rays will bend. You can see this if you're using a survey instrument and you're looking right past a building corner. You can see someone standing directly behind the building corner, but they're probably actually slightly behind that building corner, and the light waves will bend around that building. That's why it's really careful in total station surveying to not trust your eyes totally if your line of sight goes by something. When we're traversing through the woods or anywhere, and our line of sight is close to something like a tree or a building or a fence post, expect to have some angular error in that station that you cannot detect, because the light rays are bending slightly around that object the closer you get to it. If you stay a fair distance off of it, there's probably no refraction at all, or it is very, very, very minute and negligible. But I have saw where I was looking at someone holding a prism pole that looked like they were just right off the corner of a brick building, and the EDM would not shoot the distance. I could see them, I could turn the angle, I couldn't understand why, and it was because even though I could see the prism, the laser in the instrument could not, because it was hitting the building corner. Now, that's really not an issue with robotic total station, because the robot is detecting that prism as if it was in a dark room. It's just space, as if it was on the moon. It doesn't see anything. But understand that light rays bend. Now, not only do they bend around buildings, they bend around the earth. So in the bigger zoom out picture, if you're looking at a long range view, just like that rod behind the brick building corner, you may be thinking that you're looking straight at a radio tower on top of a mountain. Where you're actually looking is going to be a little bit above it. And the light rays are bending over the earth, even though you may be thousands of feet above the valley below. The earth itself is going to create refraction. And geodesists and scientists have quantified this and determined how, they've been able to figure out a formula for it. But you're actually looking down here. The object is actually down here. So here's another diagram from the book. The star is over here. The light ray travels through space, and then as it gets to the earth, that light ray beam moves or deflects, and so we think we're looking at up this dashed line at the star. But in fact, the star is over here. But if we look over here, we miss it. We're seeing something that's over here. And so the same thing that basically happens is if we're looking, along the horizon towards the sun, we're seeing the sun higher than it actually is. The sun is actually below where we're seeing it, because those light rays from the sun, if you can see this from my PowerPoint, from my pointer, the rays from the sun, and I wish they had done this, but the rays from the sun are basically coming in like that and refracting around the Earth's, probably the Earth's gravitational field. And that's what we're actually seeing. Just like here, it's deflecting to the left from this star. Then once it gets close to the Earth, that light ray will bend, and it looks like we're looking up through here, when the star is actually over here. So that's something that really, really only comes into play when you're on the long sites. I mean, like in Utah. I don't know if a place in Georgia, unless you're on a South Georgia section of I-75 or I-16, where you're really going to get into it. And we'll talk about that more shortly, how that it can become moot. One reason I bring this up, and now we're going to look at the curvature and refraction formula. Again, the scientists have made it easy for us, thankfully. They have computed all these things and got the square root of the sigma and the theta and all of these different values, and the formula for the correction in height due to curvature and refraction is formula 4.3a, which is this one right here. That is 0.574 times miles squared. So however many miles that is, square it, multiply it times 0.574, and that is your refraction and curvature and refraction, your CNR adjustment in feet. Now in meters, it's 0.0675 times kilometers squared. And you come over here, this is the one that we would use the most, 0.026 times F squared, and F is the number of thousands of feet. So if you're 4,000 feet, then this would be 4 squared, or 16 times 0.026. And so just to look at that, 4 miles, that's 5280 times 4. Well, let me back up. 4 squared is 16 times 0.0206. So in 4 miles, that's only 0.3296. So that is like 0.08 of a foot or 1 inch per mile. So that is generally negligible, and even more so with proper survey techniques, which we'll talk about in a minute. The reason I bring this up is you will likely never need curvature and refraction in your career. I never have in 38 years. I'm also not a geodetic surveyor or a geodesist, nor do I survey in Utah. But the reason I'm bringing it up in Georgia is you'll likely see curvature and refraction questions on your FS exam. So here are some examples where they've worked it out. And my picture's blotting part of it out, but for a 100-foot site, the refraction adjustment is 0.00021. So that's a tenth, a hundredth, a thousandth, 2/10,000ths of a foot, which is like micrometer reading minuteness, so small, as thin as a hair. 200 feet, it's still not even up to a thousandth of a foot yet. It's still out here at 8/10,000ths. So don't worry about curvature and refraction as long as we're doing good survey techniques, such as balancing your backsides and foresides. Next, the book jumps into differential leveling in general. So one way that they wanted to illustrate differential leveling is you set up a laser or a rangefinder, measure from the floor to the ceiling. And that is a very simple reading of a difference in elevation. Now, surveyors are not going to do that very much. That's generally more something on construction application. But what we're focusing on and what we've been trying to work towards in this module, we're finally there, sorry, 26 minutes later, is differential leveling. Now, we'll study every aspect of surveying that at least that is applicable, but this is the essence of beginning steps of surveying. And this is very simple. You set up a level. It cites a true horizontal plane. You read a rod. The rod reading is, in this example, is 8.42 feet above benchmark. That's what BM stands for in the surveying world. It stands for something different in the nursing world. BM rock has a published elevation of 820. When the level rod is placed on the benchmark, the level sees it at 8.42 feet off the ground. So the height of the instrument, the HI, capital H, capital I, HI, height of instrument, is 828.42. Now that's measured above the datum, not above the earth, because we're coming off of this elevation, which is the orthometric height on whatever datum we're working on. And then you turn around to find the elevation of point X, and you read 1.20 on the rod. So this is a great illustration without getting into math. It is this height of instrument of 828.42 minus 1.20 gives us the elevation of X of 827.22. This is what we'll do in the first lab, is go out and take some differential leveling to fully grasp how this works, the math, the application of how we do it. And the next module and chapter is all about how we do this. This module and chapter is about the theory. So differential leveling theory and applications can be expressed by two equations which are repeated over and over. First one we looked at, the HI, the height of the instrument, is the elevation of the benchmark plus the observed backside. And then when we're looking forward, we don't have to just take one to get X. We could get the elevation of a bunch of different points once our HI is thus established. And the elevation of our forward points would be the height of the instrument minus the rod reading of the foresight. So this is the essence of what we're doing. It is not complicated. And this is what you're looking at. This is a rod reading of 3.98 feet on benchmark 1, hypothetically. So, this is when you're looking through the instrument, the crosshairs are blue in this illustration so that you can kind of see better. They will almost always be black in a real instrument, and you're looking at a rod. And we'll study this more in the next section, but this is the particulars of how a rod is set up. And they call these the Philadelphia rods. There are actually other styles of rods and measurements and how they're constructed and offset, which we will not be getting into. But, here, this is the 7-foot mark, and it's the top of the wedge. The top of the wedge right here is the where 7 feet is. And every tenth you're on the top of the edge. But every half a foot, you've got another wedge, and the point of the wedge is the the half foot, or the 0.05 foot increments. And then each one of these bars is 1/100 of a foot wide. So, you know, these are great examples. And in the middle, because you might be looking, you're very likely going to be looking through the rod if you're up close, and this is what you're going to see. You can't see the 7, you can't see the 8 above. So incrementally in the rod, 1/3 of the way up and 2/3 of the way up, they put a little 7 so that you know that you're in the 7 range. So this is 7.40 right there at the top of that wedge, and that's what it says right there, 7.40. If you're down here and you're looking, well, you know, this right here, well, let's see. This is 7.20, 21, 22, 23, 24. 7.24, and you always check it by going forward or backwards to the next increment, and you see that just above it, 1/100 of a foot, is another wedge that's pointing down, which is a half a foot, so that's the 0.05. So you know that's 7.24 right here. This is 7.24. If that's your rod reading, that is where you are. So we'll do this more in the first lab. In the next module, we'll cover this more, but that's the gist of how you read a rod in differential leveling. Another method that was used in the early days is an altimeter or a barometer. And this is where they figured out that they can use the difference in barometric pressure to identify or to compute an elevation of a point. That sounds crazy to me. We did not actually study this much in my day. I don't know that it's going to be on any of your tests, but here in the book you'll see some explanation that basically, you know, we know the barometric pressure changes when there's a high pressure front that comes in, the pressure goes up. When a tropical storm comes in, the pressure goes down, and it changes throughout the day based on temperature. So the way this would work is you came to a known point and put a base barometer there. And then you took readings through the day on other distant points, and you didn't actually go by what the barometric pressure was at your point. It was the difference in barometric pressure. So they figured out over the whole Earth, barometric pressure is actually very definable and predictable. And even if there was a tropical storm coming in, you came back a month later and there was a high pressure front coming in, the barometric pressures that you read would be different, but the difference in barometric pressure from that benchmark to the top of the hill that you're wanting to measure to, that's going to be fairly consistent and can be precisely measured. And they say under ideal conditions that you can compute elevations to within 2 or 3 feet. Now, if you're in Florida, you're never going to even hear the term barometric pressure. If you're in the Appalachians or the Rockies or the Adirondacks or the Tetons, well, getting the top of a mountain close to within 2 or 3 feet is probably plenty good. So it's all relevant. Now we're moving into trig levels, or trigonometric leveling. This is pretty simple. This is the excerpt from the textbook. They use lower h, lower I for height of instrument because that is local to the point on the ground. When we're doing leveling, where the instrument is set up is irrelevant. There's no point underneath it. All we're looking for is the height of it, the elevation of the horizontal plane in the instrument. That's all we care about when we're doing differential leveling. When we're using a total station measures horizontal and vertical angles and can measure distances using an infrared laser. So that's why it's total. It can measure basically everything. And we'll be using those in the second, third labs. It's fairly simple math, but anyway, HI is the height of instrument. That would be what you measure with a pocket tape, typically just a measuring tape, or some people will use a level rod because it's straight and it's rigid and it's not going to bend. So one thing that I said I'd come back to here, and they've got this in the book. Is in trig leveling, you're basically going to take your HI in trig leveling and in total station traversing. The common industry term is plus up. That's how much you plus up from the nail, pin, benchmark, monument, whatever you're occupying with the instrument, up to the horizontal axis of the instrument. So I'm going to use the term plus up in this context. So you got the plus up, and then using trig, you can compute the vertical difference, which we'll go through in a moment, and then you take the rod height off. So you're kind of like reading a level, but it's all optical, and it's all trusting the collimator in the total station to be perfectly plumb. And sometimes they're off a little bit. They don't affect horizontal distances that much. They can have a big effect on your vertical differences. But let's take instrumentational error out for a minute. Go back to curvature and refraction. Again, this is theory that you need to know. Likely you'll be examined on it on the FS exam. But in application, as long as your back sights and foresights are roughly the same distance, and we call that balancing your back sights and foresights. You can't always do that, but if you can, what that does is your curvature and refraction adjustment for your back sight is the same as for your foresight. So they cancel each other out. In other words, you would add it to your back sight, but then you subtract it from your foresight, and the effect is zero. If you're adding, if it's a long ways off, say it's 4,000 feet, and you're adding 600ths of a foot or 700ths of a foot, but then you're subtracting it off, plus 0.07 minus 0.07 wind up being a net zero sum. So that's why it's important. Now, another thing that's important with trig leveling is horizontal leveling. You're using the optical line of sight and these eyes with your typical differential level. And in trigonometric leveling, you're not. You're letting the instrument detect that or measure the vertical difference regardless of where you're seeing it. It's reading to the prism. So anyway, the takeaway here is that the slope distance, your curvature and refraction correction will balance out and be something that you never need to use in life, as long as you're not stretching out long shots where you've got a very short sight and then a very long sight. Like if you're taking a 100-foot back sight and a 4,000-foot foresight, then you're going to need to apply curvature and refraction correction to your trig leveling. If you're able to move, which is the beauty of trig leveling, is because all you got to do is be able to see it. In differential leveling, you can't be below your benchmark or you can't see it. You're looking into the ground near it, but you're not seeing it. And you can't be more than your level rod height above it. Some rod heights are will only go to 16 feet, some go to 25 feet. So if you're too far above it and you can't see the rod, well, that doesn't matter either. Trig leveling, all you need is total station to be able to see the point. So move it out, you take a 2,000-foot back sight and a 2,000-foot foresight, you're golden. I would say that it's very good practice to direct and reverse, to shoot this vertical difference forward and reversed, and that's something we may incorporate into to the second lab, or lab 1B, for the Kennesaw students, and look at those vertical differences, because that's where your collimation error from your instrument that's not perfect will show up. You may get a vertical difference from just a direct reading to then reversing and plunging the scope and getting a reverse reading. You might get 800ths difference. Well, just take the average, because whatever error is going forward is also going backwards. It's just offsetting, or it's adding, so you compensate it by dividing it in half, and you probably get a pretty good vertical difference by trigonometric leveling. Here's simple trig leveling. This is what I was going over. You got your point A down here. You got your plus up that gets you to the height of the instrument right here. And then we'll go through this later, but using trig, your zenith angle and your slope distance, that's just nothing more than a right triangle. Nothing more. But instead of a squared plus b squared equals c squared so much, we're going to be doing a lot of this with trigonometric functions. So I can't recite it off the top of my head. I believe it's cosine of the zenith angle times the slope distance gives us v, which is the computed vertical distance or vertical difference of the observation. And so then our elevation on point B up here is the elevation of A plus our HI, or our plus up, plus V, and then minus R for rod height. And it's all just something you can visualize right here. Here's these different elevations that we're doing. Pretty straightforward. Now they give us this illustration, I think, to scare us, but this is trigonometric leveling along the lines. This is where you have just long lines and not balanced sides. This gets a lot more complex because you have line of sight, you have refraction, you have curvature of the earth. You've got the refraction coming up here where you're actually looking at the rod. You got the curvature going on everywhere, so they just take it and put it down here off the horizontal line, which makes sense. You're coming down here. But we're not going to be concerned with that or the math, which gets to be more complex with curvature and refraction correction to long line trigonometric leveling. Let's talk about some levels. If we're doing differential leveling, the book will tell you there are lots of different kinds of levels that have been used over the years. Besides trig leveling, the two most common, possibly exclusively used in the surveying world, is an auto level and a digital level. So here, this is just your typical auto level. There is a compensator that's hanging freely in here. We hope, and we hope it's working correctly in theory, and that's how they're working. You set this on top of the tripod, get the tripod good and steady. If it's moving, your eye's moving, you've got bogus readings. But you're going to have leveling screws on the tripod. You're going to have a bullseye bubble we'll talk about in a minute. You know, this is the objective lens where you're looking. This is where you're going to focus, and you're going to have usually have a little bar like a rifle sight or a pistol sight that's going to be able to point you where you're looking, and then you're looking through the eyepiece. Now, this is all pretty simple. Now, the book in the later part of this chapter, they start talking about capstan screws and things on adjusting these. I'm not going to cover adjusting instruments. All of my career, I've taken instruments to dealers and repair shops where that's all they do and they know what they're doing. I have worked places where people tried to adjust their own instruments and they would break things internal. Then the instrument's down, and then you have to pay more to have it fixed. So have your instruments routinely calibrated and checked like once a year. And if you think you've got a problem, take them somewhere. Do not try to fix them yourself. The way an auto level works is you got this compensator that's hanging in here, and it's got a bunch of really nicely, real precise mirrors and lenses and things that even if it's out of level a little bit, you still wind up getting a level line of sight through the level. So it doesn't have to be perfectly level. This is the bullseye bubble. We'll look at this in class, but it's a bubble on the top side of the instrument. You use the adjustment screws to get the bullseye in the middle. And then what that means is you're level. Because if the bubble's not in the middle of the circle, it's over here, which means it's leaning. But when you get it perfectly level, the bubble's in the middle. Now I say perfectly. We're plus or minus 20 seconds of sensitivity angle at a 68-foot height above some imaginary datum, which just means they're pretty accurate. But I'm going to stop for a minute and talk about old levels, like dumpy levels, to where you have long level bubble piles. And this could be a cross section. The illustration is accurate for what a cross section view of a bullseye bubble. It's also basically what you're seeing on a tube level or a dumpy level. And that's where it's been calibrated in a shop very precisely so that you're once it's really, really tight, then you're plus or minus 20 seconds at 68 feet. Now, I guess that's something that came over from England, but while they decided to measure in that realm. But you have to get in a dumpy level, not an auto level, but where you're actually making the line of sight perfectly level with adjusting on bubbles. It's a lot easier to be off a little bit, and off a little can amount to a whole lot on your sight. That's why we like auto levels. We also use digital levels, just like your barcode or your QR code. Many years before those were as common, instrument manufacturers figured out how to create unique, really long barcodes on rods, which you see here in the bottom. And it's got an auto level compensator in it, and the level knows how to observe this barcode and determine exactly where on that rod the level line is from the combination of its compensator and how it's reading and capturing the look at this 6 foot long barcode that's strung up a rod. And it does exactly the same thing as a human eye looking at a level rod. It just gets a reading on how high above the ground the horizontal line of the digital level is intersecting it. A hand level, I have one. I haven't used it in years. It does the same thing. It's like 6 inches long, but it's not very accurate because it's not supported by a tripod. But they can come in real handy, especially in steep terrain, or maybe not even in steep terrain. Rather than take the time to set up your level, get your bullseye bubble level, get focused, and then jump on it. Rather than do all that, you can get your level rod out, you can get your hand level out and look and be like, oh, I'm below that, so I have to move up the hill. Okay, I'm gonna need my, once you're above your benchmark or whatever point you're looking at, then you can figure out where to set up the level so that you can see it. Or if you're in steep terrain, you're like, hey, put the rod all the way up, get your hand level out, you're looking 5 feet over the top, you gotta come back down. It also has applications in some rough construction staking for roads, rough grading roads. You can get close enough to start having a bulldozer or a trackhoe move a lot of dirt, but today they're probably going to use machine control and a GPS file. This figure just shows various rod types. We've already covered that a little bit better in my opinion, but this was in the Pearson provided slideshow, and we're going to conclude with a discussion about parallax. Parallax is a problem that is avoidable, but that can create big problems with your leveling, whether if it's or any surveying that uses the eye and a crosshair and a telescopic lens. If you've shot guns before with a scope, you may have experienced parallax. Parallax is where your eye thinks that everything is focused and nice and crisp and happy, but it's not. It's very hard to detect. That's why when you have parallax, you have measurement errors that were not detectable, were not the instrument's fault, were not systematic or random. They are human errors. They are avoidable errors. And so we have a hard enough time controlling the various factors that create errors in survey measurements. So we need to first, with any instrument, and we'll do this in the labs, is make sure we don't have parallax. And this will change from each person's eyes. Whether if you have great natural eyesight, mediocre natural eyesight, or poor natural eyesight, whether if you wear glasses or contacts, parallax is going to be different for everybody. So if we're in lab, you're looking through a level, the next person behind you, before they take a reading, they need to check for parallax and go through the steps. It's not that complicated. So here's what we're looking for. We're looking through the eyepiece, and here's the focus. This is for the objective lens. We're going to focus what we're looking at right here. We also have a focus on the eyepiece. The eyepiece focus adjusts the crispness of the crosshairs. the big focus over here adjusts the focus of the object. Now, in theory, if both are crystal clear, you should not have any parallax, but that's not always the case. So what do we do about it? How to discover if you've got parallax is move your eye up and down. And they've got a nice little diagram here. They've got a video on the Pearson instructor page that I'm not sure how to share. It's not that long. It may be available to you in the ebook or the day one book. So if it is, it's a good little 6-minute video. But you move your eye up and down and the object will appear to move with respect to the wires. I say crosshairs. What's going on there? Okay, that means that you're really not in crisp focus. You might be looking at your crosshairs fine, you might be looking at the object fine, but you know the instrument's not moving and you know your object's not moving. If you move your eye up just a little, up and down, if the point of focus of the crosshairs moves on that object, you have parallax error. And you need to leave your object in focus, but go to your eyepiece and adjust the crosshairs until when you move your eye up and down, the object doesn't move. And this is how to correct it, what I was just saying. They say carefully focus the eyepiece and objective lens until both the crosshairs and the object are crisply focused. Move your eye up and down to test the focus and look for the object moving. Now, as I said, the last parts of this chapter, the author talks about instrument adjustments and how to adjust your levels, and I'm not covering that. I don't recommend that you do that. There is, however, one part of it that you may see on the FS exam, and the book doesn't call it, but we would call it the 3-peg test or the 2-peg test. And that's where you get out, and what they're calling it is figure 4.22 horizontal collimation test. So you set the instrument up over here and you want all these sights to be equal distance. I even say take a tape measure. You don't have to take a total station to get to the 100th, but at least take a tape measure and get within a half a foot or a foot of being 100, so that any error, any focus, any systematic error is duplicated, coming and going, and everything's a nice consistent 100 feet apart. You'll set the level up first over here on point 1, and you want to take a reading on point A and point B, and your line of sight is going to be up here. Just say you have some error. It's this top solid line. The actual horizontal line, due to the error, is this dashed line. And so in this case, your line of sight is above the actual horizontal, and that should be consistent throughout wherever you're setting up the level. And I'm only talking about auto levels, because if you get into bubble adjustments on dumpy levels, you get into a lot of weird stuff, and nobody makes or uses dumpy levels anymore. Then you go over here, next you go over to point B, which would be 300 feet away, and you shoot back on A and B, your 2 pegs. And this will tell you if, in theory, at 100 foot, you should have this error. I can't remember exactly what E stands for. It's your collimation error. It's E. It's error for collimation. Collimation just means when things are out of adjustment inside the instrument and they're not what they're supposed to be. They're not truly vertical. They're not truly horizontal, whichever plane you're measuring. So in this case, your 100 foot collimation error E is going to be doubled out here, like if. And you don't know that until you have a check, because as long as you're using the same instrument, if it's level, 2E and E, they balance out and it's 0, and these lines are the same. But if they're not, it's just like with trigonometric leveling, where you get the vertical difference from A to B and then from B to A. If you take the average, it's taking out the instrumentational error if you've done everything else perfectly, in theory. Here, this is kind of similar to that, in that at 200 feet, you're going to have twice the error that you do at 100 feet, obviously, but you're going to have a difference between A and B from one setup to the other that's going to be reflective of the collimation error in the instrument. And then, using that, you can adjust the instrument or say, it's out of adjustment, we need to take it to Geotronics or Allen Precision or wherever you go to get the instrument adjusted. So this is call it the two-peg test. I personally had a two-peg test question on my LSIT exam, the predecessor to the FS years ago, and that's something that you can look for. Now, this lecture is longer than usual. I definitely try to keep them below an hour. In survey one, I shoot to keep them around a half an hour because it seems like the attention span is a little bit less, but I try to be thorough and cover everything that I can. Lastly, this material is copyrighted. It does come from the Pearson textbook, copyright 2022. Thank you for watching. I hope this is helpful. See you next time as we dive into Module 4, Chapter 5, and get into some actual differential leveling field techniques and computations. Thank you.